Okay, let's just dive right into this. 81%. According to the latest projections, that is the staggering slice of global AI accelerator revenue that NVIDIA commands. And look, if you zoom in purely on the data center GPU market, some estimates push that dominance up to an unbelievable 92%. That's not just a market lead, right? That is absolute, undeniable gravity. But of course, here is where the friction starts. You literally can't command that much of the future without painting a massive target on your back. As we look at the landscape today in 2026, the hyperscalers, we're talking giants like Google, Amazon, Microsoft, they are pouring billions of dollars into their own custom AI silicon. They want lower costs, they want more control, and they desperately want to break free from relying on a single vendor. So the stage is set for this massive clash. And if you're operating in this space, you really have to wonder, how do you even begin to compete with that? Well, welcome to this explainer. Today, we're going to look at the data and figure out exactly why unseating this giant is just profoundly difficult. We aren't going to look at NVIDIA simply as a company that makes fast chips. We need to understand it as a deeply entrenched, highly integrated platform moat. A fortress, really. So here is our roadmap for deconstructing this fortress. We'll start with their foundational philosophy of extreme co-design, and then we'll break down the 4 self-reinforcing walls of their moat. All right, Section 1, Extreme Co-Design and how they eliminate bottlenecks. So to really grasp this moat, you have to make a fundamental mental shift. The true unit of compute is no longer a single chip. It's the entire data center. If you optimize a GPU in total isolation, you've already lost. Everything NVIDIA does is anchored in a principle called Amdahl's law. In an AI data center, you've got thousands of processors working together on these massive problems, right? Amdahl's law essentially states that your system's maximum speed is dictated by its slowest bottleneck. It absolutely does not matter if your billion-dollar GPUs can calculate at lightning speed, if they have to wait for data to travel across a congested network, or if the memory bandwidth is just too slow, those incredibly expensive processors are just sitting there painfully idling. Think of it like a massive superhighway. It doesn't matter if your cars can go 200 miles an hour if the off-ramp is a dirt road. Adding more processors gives you diminishing returns if even a tiny fraction of your workload is bottlenecked. And this is exactly why NVIDIA structures itself around extreme co-design. They simultaneously optimize the compute, the networking, the memory, and the software, so no single layer ever constrains the others. You can't just build a fast chip anymore, you have to build the whole machine. Moving on to Section 2. Accelerating hardware cadence and the tokenomics of AI. Think of the modern data center as an AI factory. The raw material is electricity, and the finished product is the AI token. So the fundamental economic metric that matters to the people running these factories is throughput per watt. To protect this factory and keep customers locked in, NVIDIA maintains this punishing annual architectural release cycle. We saw Hopper in 2024, Blackwell and Blackwell Ultra in 2025, and now the Vera Rubin platform launching in the second half of 2026. They are forcing competitors to chase a constantly moving target. By the time a competitor finally gets an alternative chip to volume production, NVIDIA is already shipping the next generation. And just look at the sheer scale of the generational leaps here. When operators upgraded from the Hopper HGX H200 to the Blackwell Ultra Rack system, they saw up to 50 times more throughput per megawatt for inference workloads. 50 times! Because a data center's physical facility costs are largely fixed and sunk, plugging in hardware that is that much more efficient immediately skyrockets your return on invested capital. It essentially forces a recurring upgrade cycle that competitors simply cannot outrun. Section 3. The dual networking moat. Connecting the cluster. Okay, so in AI, communication speed is just as critical as computation speed. Networking is a massive performance multiplier, and NVIDIA totally dominates 2 distinct planes here. First, there's scale-up networking, which happens within a server rack. Using their proprietary NVLink and NVSwitch, they tightly couple GPUs into a single unified memory pool. Hopper connected 8 GPUs at 900 gigabytes per second. Blackwell scaled that to 72 GPUs at 1800 gigabytes per second. The 2H26 Vera Rubin architecture will double that again, and the Rubin Ultra in 2027 will connect an insane 576 GPUs into a single unified brain via its NVL576 Kyber architecture. Then, on the flip side, you have scale-out networking, which connects those racks across the entire data center using quantum switches for InfiniBand, which is great for low latency, and Spectrum X switches for Ethernet. The reality is, AI requires both of these layers working seamlessly together. NVIDIA is literally the only merchant vendor that owns this end-to-end fabric.
And a lot of that is thanks to their brilliant $7 billion acquisition of Mellanox back in 2020, which has now exploded into a roughly $31 billion networking business for them in fiscal year 26. Think about it. If a challenger builds a custom AI chip but doesn't have a comparable networking fabric to connect thousands of them together, that custom chip simply cannot scale to frontier AI workloads. It's a non-starter.
Which brings us to Section 4, securing the supply chain and controlling the physical choke points. Taking us out of the digital realm for a second, actually building these systems requires incredibly constrained physical resources. Securing advanced CoWoS packaging from TSMC right now, it's basically like trying to get VIP tickets to the most sold-out concert of the decade. Demand is outstripping global supply by 40 to 50%, but NVIDIA's massive scale guarantees them front-of-the-line VIP priority allocation. And it doesn't stop there. They also consume over 50% of the global output of high-bandwidth memory from a very tight supplier triopoly, all locked down through pre-secured multi-year agreements. All of this points to an absolute reliance on TSMC, which commands roughly 90% of the global leading-edge logic production. NVIDIA leverages its sheer size to lock down these fabrication nodes. While Blackwell utilizes TSMC's 4NP node, NVIDIA has already secured TSMC's 3-nanometer capacity for their upcoming Vera Rubin architecture, and that capacity is reportedly committed all the way through 2027. So even if a competitor designs a genuinely better chip, they simply cannot get the advanced fabrication, the packaging, or the memory required to actually manufacture and ship it in high volumes. The physical supply chain itself is just an insurmountable barrier. Finally, Section 5, the software ecosystem, developer lock-in, and platform absorption. You can have all the hardware in the world, but developers need to actually be able to use it, right? This is where CUDA comes in. Launched way back in 2006, NVIDIA's software ecosystem has grown from 2.5 million developers in 2021 to over 7.5 million by 2026. Major AI frameworks natively optimize for it. Combined with their CUDA X suite of over 400 proprietary libraries, it creates massive technical and institutional switching costs for anyone trying to use alternatives. Plus, NVIDIA uses this software aggressively to attack bottlenecks. Take their Dynamo open source framework, for example. It smartly separates the two phases of AI inference, the prefill and the decode, across different GPU pools. This software optimization actually raises throughput without customers even needing to buy new silicon. And let's look at how all of this builds into their ultimate defense strategy against those custom chips we talked about at the very beginning. If a competitor builds an ASIC that's incredibly good at just one specific task, NVIDIA simply absorbs that technology into its platform. Look at the upcoming Vera Rubin pod. NVIDIA licensed language processing unit technology from Grok, creating this amazing heterogeneous supercomputer. Uses NVIDIA's Rubin GPUs for the heavy compute phase and Grok LPUs for the ultra-fast text generation phase. By integrating these together, they are pushing the throughput per megawatt frontier up to 35 times further than even their own Blackwell NVL72 generation. They literally just swallow the custom silicon threat whole. So we've seen how extreme co-design across compute, networking, supply chain, and software creates a deeply entrenched, self-reinforcing moat. Hyperscalers are certainly fighting back with their own custom chips to cut cost, for sure. But as we look at the reality of data center economics in 2026, I want to leave you with this final thought. When the true unit of compute is the entire data center, can an isolated custom silicon chip ever truly breach a fully integrated, co-designed AI factory?